Hi, recording is rolling. It's Tuesday, February 14th. So I have a PowerPoint for you guys today. It's on materials and properties of materials. So, well, here's a bunch of stuff we're going to be looking at. So I will skip over here and let's get going on that. So materials and states of matter. So kick off here with the scaling, which is going to be connected to one of the slides coming up about a thermal expansion. Right? Like if you heat something up, it's going to expand. Usually, right? Now, there's a couple of weird exceptions. Like I know water at some temperatures, you heat it up and actually contracts, or like you guys know, if you freeze water, it goes from a liquid to a solid, it'll actually expand. Now that's a weird exception. Most materials, if you heat them up, they occupy more volume. So what's like the mathematics behind this? I think you guys may have seen this or something like this last semester, but it's a good review. So let's say I have a little tiny box here, a little tiny box, right? And I'm gonna expand it in 3 dimensions by like a factor of 3. Right? Now that's just what I'm showing on the slide, but you could expand it by any factor and figure out from there how all these other properties are going to change. So anything that's linear is going to also expand by the same factor, in this case, factor 3. So 3 times as wide, 3 times as tall, 3 times the depth back into the page. Also, how about this? How about 3 times the perimeter? Like if you walk around a small box versus if you walk around this large crate, right? That would be 3 times the distance. Okay? So anything that's linear in nature is going to expand by factor 3. What about something though, like how much paint would it take to paint a box? So if you paint one of the small boxes, it takes some amount of paint. Okay? How many more times of paint to paint the entire crate, surface area of the crate? Well, that's an area concept. So that linear expansion factor, I'm using Greek letter lambda to represent that. There's nothing really special about that character though, just for the slide, I guess. Okay. All right, well, that linear expansion factor of 3, square that, you get 9 times. So take 9 times the paint. So anything related to the surface area, 9 times the surface area. Okay. One application of this fun application I remember is from Paul Hughes' textbook. He asked a question about like why do elephants have such large ears, and it has to do with like radiating heat away, right? Because they'll have like so many times the area, right? Actually, if you scale up the size of animals, like from going from like small rodents to like big elephants or something, right? The proportions of area and volume and anything linear change differently, right? So if you like 3 times the height, you have like 9 times the surface area, but look at this, you'd also have like 27 times the volume, like 27 times the mass. You guys see you can fit like 27 small boxes inside the large crate, right? If I said like how much water could you fill in the small box, how much water can you fill in the large crate, that would be 27 times. So you have 27 times the mass, 27 times the weight, all that, right? Now that's actually the mass and the weight doesn't exactly apply to like thermal expansion, right? You don't change the mass of the weight of something by heating it up, right? But it would change its volume by something like that, right? So something expands by some percentage, right? Something like that, right? Okay. And okay, yeah. Let's go here. Had some videos, but these are like Paul Hewitt videos that you guys saw the other day, so I'm just gonna skip past this. Actually, here I should have this slide first. So here's thermal expansion right here. Thermal expansion. Okay, so maybe you got a bar of something. Maybe it's a steel I-beam, for example, or maybe it's a concrete block. Okay, so some original length. You guys see L naught? That could be original length, right? L naught is original length. Okay, and then maybe you heat it up. Okay, and it's going to expand by some increased amount. Oh, that's what delta L is, right? Like a change in length. That's what delta L, change in length, right? So how much will it change its length? That's delta L compared to its original length, L naught. Well, it depends on the temperature change. That's what delta T is, right? Delta T. That could be in degrees Celsius. That could be in Kelvin. You could also do Fahrenheit, right? If you're talking about some temperature change. Quick review, guys. Is a change in 10 degrees Celsius the same thing as a change in 10 Kelvin? Yeah, because those two systems are scaled the same, right? What do you guys think this alpha refers to?
The amount of expands for temperature,
Okay, yeah,
the rate of expansion.
yeah, and this is a material property. You see somewhere here, the linear expansion coefficient. Okay, so it's called the coefficient of thermal expansion. But this is what will distinguish, say, like a steel I-beam from a concrete block, right? Like some kind of alpha factor, which, by the way, side note, concrete and steel have almost the same alpha. It's just complete coincidence that that's why you can make steel reinforced concrete. So it's coming up eventually in this class. But yeah, so this is really a material property, right? So some materials will expand more than others for some given temperature change. I see something like that. Okay. Okay. You guys get that okay? Some textbooks have this equation written a little bit differently. So you might take this L naught and divide it over, and you get delta L divided by L naught. That would be like a percentage change in length. You could call it strain, sort of a similar concept, like the percent that it changes, right? It's length. So yeah, anybody going to civil engineering, you're going to see all this tech stuff. I've also got a whole engineering PowerPoint lined up for one of these days. Okay? So let's go back to this one. Now this is one that Paul Hewitt showed you guys the other day, so everybody should know the answer to this one. You guys know if you heat up a metal ring, well, if you heat up a metal bar, it's going to expand, right? So if you heat up this metal ring, I bet the material itself is going to expand. But what was the answer to the question? What happens to the size of the hole? Does that expand, contract, or stay the same size? What was the answer? Yeah, it also expands, right? As long as you heat it uniformly, that's going to be true, right? So the entire system is going to expand. It's like just blows up, including the hole. The hole actually becomes larger there too. Okay. All right. So let's get past some of these. Okay. All right. So we're going to be looking at a lot of these principles of. I guess we're going from like solids to liquids here. Right. So we're looking at properties of like liquids and fluids also. So Archimedes principle. Right? If you've ever been swimming, say in the ocean in a pool, you guys know there's some kind of upward force, right, that's letting you float. And what that force is equivalent to is the weight of the fluid that you are displacing. And so more often than not, we're dealing with water. Sometimes I'll say like the weight of water that you displace, right? Because it's been water, right? This was another Paul Hewitt demo that you guys saw. I might rig up a lab that's really this one of these days too. So say you're hanging a weight in the air and it weighs like 4 newtons. Okay? Now, if you want to be strict about it, there's a tiny, tiny buoyant force from the surrounding air because air has a little bit of density. And so there's a tiny upward force, but with our high school equipment, you can't really like measure that quite. Right? So this thing basically weighs 4 newtons, right? Right, then you dunk it in the water, which has about 1,000 times the density of air. So whatever the buoyant force was in air, now it's 1,000 times that. So now that is going to matter. Okay, can you guys look at this and tell me what is the buoyant force equivalent to? From here to here, what's the buoyant force equal to? Not 1 Newton. Yeah, 3 newtons, right? You guys see 3 newtons, right? Because this thing weighs 4 newtons. And then over here, the tension's only reading 1 newton. So there must be an extra 3 newtons supporting it from somewhere. That's the surrounding fluid, like the surrounding water, right? See, it's like it's occupying a void where water wants to be, and water wants to like push it somewhere, right? So it's gonna push it up. Let me skip over here. I'm gonna flash back and forth this presentation and fill you guys in with some notes. Oops, put my screen so this video works too. All right, here we go. Okay, so we got state free body diagram for exactly what you guys just saw. Right, so like there's some block. Okay. Now, when the block was hanging out in the air, the free body diagram pretty simply was this. There was a weight down, and there was the tension force up, which was being read as the spring scale. Okay, that was 4 newtons, so that was 4 newtons. But in the water, well, did Earth's gravity pull change at all on the block? No, it's the same weight. Right? Earth still pulls on the block the same way, so that didn't change. Okay? But the tension force was only reading like 1 Newton. Okay? So that tension force is really small. Okay? But it was still in equilibrium. Right? If it wasn't moving, right? The force had to balance. That's where this F sub B, the buoyant force, comes in. So that's the free body diagram for the picture on the right. Okay? And so, oops, that was let me draw some water just for context here. This could be like water here, right? Something like that. Got a glass of water. So that buoyant force, F sub B, is equal to the weight of the displaced water. Right. And that fact right there is called Archimedes principle. There's this whole story of you guys might know the story. There was like a crown that was purportedly made of gold, and some king of the city state was skeptical of this. So it was known, hey, we could know if it's gold or not by getting its density, but how do we get its density? And this problem was going to Archimedes, and he went home and was in his bathtub thinking deeply about his problem. And I was like, hey, when I like submerge myself down, it like displaces a certain amount of water, and I can figure out density from that. That's come out here pretty soon, this idea of density, right? Because if you know like a displaced volume, then that's how you can get the volume of this weird crown shape. And you can get its mass pretty easily just by putting it on a scale. If you know mass and volume, there you go. So they went and tested it. It's like, oh yeah, the crown actually did not have the density that would match gold. So it's trying to be the case. Okay. So the weight of displaced water, I could write that like this. The mass of the water times the gravity field of the planet, right? M times G. That's what weight's been all last semester, right? Right. So weight is mass times gravity. And notice I'm not saying the mass of the block itself. I'm saying like the surrounding fluid, right? You say the mass of the fluid times gravity, right? Like that. And let's go one more step with this. And this is where density is going to come in. So here, with this. Do you guys know density? I got a question for you guys. I hope you guys know this, but if not, I guess that's why you're in school. Okay. If I got, yeah, there you go. That's what I was going to ask, guys. Yeah. Mass per unit volume. Okay. And see, this is like a material property, right? So if I have like this block here, whatever metal this is, okay, it's 1 kilogram of mass, it occupies some amount of volume. And if I divide those two, that's okay, that's the density of this particular material. Maybe I could open up a textbook and say, oh, it must be like brass or something, right? What if I had a styrofoam block that was like the same volume? So it'd be definitely less mass, but same volume, so it'd have a lot less density, right? Right. Now, a lab you could do with those, and we might do a lab activity. Hold on a minute. Yeah, we might do a lab activity kind of like this one day. Is what if I have a glass of water and I dunk some object in it, and it moves the water line like up here? Okay. Do you guys think that the volume of the object is equal to that displaced volume? It's the same volume, like whatever volume that is, that's the same volume, right? Okay. And then if you know the mass because you throw it on a scale, and you know the volume because you watch the water line being displaced, right? Divide this to get the density. Okay. Now the physics characters for this, the variables, density is represented by a Greek letter rho, looks kind of like a curly T. Okay, that's that. Okay. And then you guys know mass is M, volume could be capital V, be like that. Okay. Now, could you rearrange this and make it look like this? Mass is equal to the density of some material times the volume of that material. That could be true too, right? So whatever density, just like the density of zinc is blah blah blah, okay, times the volume will tell you how massive it is. Okay. So I'm going to take that right there and substitute it right here. So instead of mass of water, what if I do the density of the water times the volume of the water that displaced. Okay. And then of course we've got times G to turn into like a force. Okay. It could be like this, right? There you go. That is what buoyant force is equal to. It's the density of the surrounding fluid, which could be water, okay, times the displaced volume, okay, times the gravity field. Now in this example, this block is entirely submerged. So the displaced volume is equal to the volume of the object. But that's not necessarily true. We're going to look at icebergs in one of these upcoming slides. And an iceberg is partially floating, and the part above water doesn't displace any water. Only the part that's submerged is. Okay. That makes sense. Okay. All right. So hold on to the city because we're going to add to this. So flip back over here. All right, let's get another look at this right here. Okay. So you guys see a change in 3 newtons from left to right. So there must be 3 newtons of support force. And if you capture all that water, just like you guys saw Paul Hewitt do the other day, oh, look at that. The weight of the displaced water is in fact 3 newtons. Boom, there you go. Okay, Archimedes principle. Okay, you guys get that? Oh, here's the iceberg. So free body diagram on that iceberg, it's got a weight acting down and a buoyant force acting up. It's keep it in check, so it's in equilibrium. Okay. Side note here, icebergs are almost all drawn like this. When I went look around the internet to find an image, they'll, but actually, strictly speaking, that's not actually a stable orientation. So the iceberg is always going to want to fall down on its side, right? It's just like a stability type thing. But I don't know, I guess the cartoon versions always look like that. But you can ask a question like, hey, I wonder what percent of the iceberg is submerged, and what was the percent that you actually see above the waterline? Have you guys ever heard if you see an iceberg, you're really only seeing the top 10%, and the other like 90% is down underneath, right? Which is actually pretty close to true, right? But what's the physics that could back that up? How's that related to Archimedes' principle? Like, could you derive that? Well, we're about to, right? Right. So let's switch back over here. Now, what you'd have to know are the densities of these materials, because different densities are going to correspond to different levels that it will float in the water. Okay, so here's the question: is what percentage of an iceberg is submerged? Right. Let's say like how much is actually underneath the waterline, okay, which you guys know probably just anecdotally, if nothing else, should be about 90%. That's kind of what we should be looking for, about 90%, right? Okay. And the values you have to know to be able to solve this. Here, I'll give you guys the density of ice. I'm going to use kind of a round number. This isn't exact, but I'll say about 900 kilogram per cubic meter. Okay. And let's say the density of water. Now, if it's fresh water, this is what they were designed the whole metric system around. It should be exactly 1,000 kilogram per cubic meter. That's not exactly true for salt water. Salt water is more dense than that. So it's like 1,030 or something like that. But we're just going to round these numbers a little bit. Okay. So how can you show the answer to this question? So let's get ourselves an iceberg. Okay, it's floating here. There's a water line. Okay, so we got water here. Okay, let's do a free body diagram and then start deriving this thing. Free body diagram. So I'm thinking two forces, okay, and they should be exactly balancing each other out. We have the weight acting down. There's your mg. We got the buoyant force acting up. F sub b. Boom, like that. Okay, now let's break these down a little bit more, because I just told you guys a few minutes back that buoyant force should be equal to the weight of the displaced water, which should turn into the density of the water times the submerged volume. Submerged, okay, which is like, here, I should hash that in. You guys see that hashed in volume, right? That's only that it's actually submerged. It's actually displacing any water, right? We should say displaced volume. Oops. Right? Times the that's gravity field. Right? So there's the mass of displaced water, and there's the weight of displaced water. And then, see, I could do something really similar for the weight of the ice, right? M times G, the weight of the ice. Because couldn't I take the mass of, here, this mass is talking about the mass of the entire iceberg, isn't it? Mass of the ice. Okay. Could I break that down into density of the ice times volume of the entire iceberg? And then this G is still this G. I could do that too, right? Okay. Now these densities are different densities. This is the density of the ice. This is the density of the water. These volumes are different volumes. This volume is the entire iceberg, because the entire volume of the iceberg contributes to its weight. This volume is only that hashed in volume that's just pushing water out of the way, right? You guys get that? Okay. And then G is G. Okay. So I can say this is equal to this. You can do that too, right? You guys get that? Okay. So let's go ahead. Let's set those equal to each other. Well, I mean, I guess I could say this minus this is equal to 0, but then the next step would just be density of the water times volume displaced. I'll call this displaced. Displaced. Okay. Times gravity field is equal to this expression, density of the ice times volume of the ice times the gravity field of the thing. Okay. So that could be the setup right there, right? Okay, so far? Ooh. And guys, what's going to cancel out on both sides? Gravity field of the planet, right? Okay. So remember, whenever something cancels out in physics, think what that means. It means you could take this whole system to Mars and you should get the same solution, right? That should be the same answer, same outcome. Now, you need gravity to make this happen, otherwise everything's just kind of floating around. But once you have gravity, it doesn't matter how strong gravity is. Okay. Okay, now here's where you have to be a bit creative. that question, what percentage of the iceberg is submerged? You can get that from the setup. Little bit of algebra switch around. Okay. Do you guys see that that question is really asking what is this hash gen volume compared to the entire volume? Right? That's the same way of saying that same question, right? Okay. Wouldn't that be like this? What is displaced volume compared to volume of the entire iceberg? Right? Isn't that the target question? That's that, right? Okay. And you can take this setup and just rearrange it. And wouldn't that be the same thing as see, this divides down there, this divides down there, density of the ice divided by density of the water? That's what that would be, right? And look at the given values. I told you the two densities. I told you the density of this material, density of this material. Okay. So now all you got to do is 900 kilogram per cubic meter divided by 1,000 kilogram per cubic meter, which is equal to 0.90, or if you like, 90%. Boom, just like that. All right, move it through. All right, you guys got that? All right. Yeah, while you guys are write that down too, you know what I hadn't exactly addressed so far is why the buoyant force is directed upward. Why is it that you jump in a pool and the force that pushes you up specifically? Why doesn't it push you down to the bottom of the pool? Okay. Pressure increases. You guys know if you jump in a pool, if you dive down to the deep end, the deeper you go, the more the pressure builds up. So pressure from the water is equal to the density of water times gravity field times your depth. So I'll call it H, like depth in the water. Okay. So the deeper you go, the more the pressure is. Okay. And the fact that objects are three-dimensional. Okay. See, water pressure acts in all directions, and it acts like perpendicular to the surface of some object. So if you have like some weird shaped iceberg, right? Why is this outcome like 90% is going to be submerged? Why is that like independent of the shape? Okay. Well, you got water acting like all different angles, blah blah. Okay. But it all cancels out except for the fact that there's more pressure on the bottom than on the top of the object, right? Because of this right here. So the fact that the bottom of the iceberg is deeper than any other place, right? There's a lot of pressure on the bottom pushing straight up. Okay. And near the surface, there's a little bit of pressure, and maybe like pushing to the side or something, but all the side stuff cancels out. Okay, see that? Okay. So there you go. So that's something to do with the direction of the buoyant force. That's why it's upward. Okay. You guys go with the iceberg? Oh yeah. All right. Let's head back over to the PowerPoint. Okay, so this classic example of Archimedes' principle. Ooh, Pascal's principle. Right, so a couple ways you see Pascal's principle written out. I actually like the second bullet point here. This way I think of it, equal pressures at equal depths. Suppose you're like a fish swimming around this fluid, or like a diver swimming around the fluid, right? It shouldn't matter if you're on the left side or the right side of the system. You should feel an equal pressure and equal depth. That would have to be true, right? Okay. All right, so how about this top bullet point? Sometimes you see it written this way: pressure is transmitted without loss throughout a container. Okay, so all right, so if the pressure is all the same at the bottom of this system, okay, so we got that. Okay, that would also be true as you start to work your way, say, up into these sides right here. So if you go like 1 meter up here at this level, and at the exact same level on the other side, again, it's also equal pressure, right? So we got the same pressure everywhere. Okay, now you guys know pressure is force per unit area. You guys remember that from last semester. Okay, do you guys remember the unit for pressure in the metric system? Pascals. Yeah, and 1 Pascal is the same thing as 1 Newton per square meter, right? Right, you guys remember, does anyone remember the atmospheric pressure we're in right now? How many pascals that is? It's about 100,000. It's like 101,000 pascals, right? Yeah, so there you go. So force per unit area, right? And that force per unit area, right, it's the same at equal depths. And in fact, if this pressure is under if this fluid's under a lot of pressure, proportionally, it might not be a whole lot different from the bottom to the top either, right? So like that. Okay. Okay, so the fact that we have equal pressures, hey, can you rearrange that pressure equation in terms of force? Could you say force is equal to pressure times area? That's just a little bit of algebra switch around, right? Force equal to pressure times area. Hey, that could be like this, couldn't it? Okay, so now we're thinking about forces. Ooh, I know one kind of force could be weight. Hey, maybe I want to lift this whole vehicle right here, lift this whole car. Ooh, that would be a lot of force. you can actually do that with a really small input force. And that's what you guys are looking at is called a hydraulic lift, right? So this is called a hydraulic lift. And this operates using Pascal's principle. I mean, I guess the physics principle is Pascal's principle, right? And the engineering application is hydraulic lift. Okay? So if you have a very small force on the left side, right, acting over a very small area, that's going to correspond to like some pressure on the left side. Right? That could be equal to on the right side with that large area. So the same pressure or very close to the same pressure times a large area is going to correspond to a large force. So you can lift something that's like 10 times as, you can magnify your strength by like a factor of 10 if you have 10 times the area. So if the areas of these two pistons are like 10 to 1, right? So if this has 10 times the area of this, you magnify your strength by a factor of 10. Okay? Now there is a catch with this, and that's has to do with displaced volume. So do you guys see here? Okay. Yeah, thanks. Do you guys see if you push the piston down on the left side, suppose you push it down like 1 meter deep, and maybe the area is 1 square meter, so that would be 1 cubic meter that you displace. Wouldn't it also be 1 cubic meter displaced fluid on the right side, but now it's pushing the vehicle up? Right? But then if you divide that 1 cubic meter by 10 square meters, because that would be the area, well, now it only goes up like 10 centimeters. Okay, so even though you're 10 times as strong, you have to push 10 times the distance to lift the car. You know what this reminds me a lot of are your pulley systems from last semester. You guys remember your pulley systems? Okay? So you could rig up a pulley system to get a mechanical advantage. Maybe you had a 3-to-1 mechanical advantage. You're like 3 times as strong as you would be. Okay? But the catch was you had to pull 3 times the string. You guys remember that? So like energy was still conserved. Right? You guys remember that? Right? Yeah, so this is, there you go, Pascal's principle. Right? You guys got on Pascal's principle? Oh. All right, this next one, Bernoulli principle. Actually, there's a couple of things. I want to show you guys this one, Bernoulli principle, but I need to lead into that with conservation of flow. All right, so this takes a bit of setup. So I'm going to switch over back to my notes. Okay, notes here. Okay. So before I actually get to Bernoulli principle, let's first do, what's this? There. Okay, I'll do something else first, which is conservation of flow. Yeah. All right, so maybe maybe I have a large pipe leading into a small pipe, or maybe I have a small pipe leading into a large pipe. Could be either way. Maybe I'll draw both for you guys. How about that? Okay, so you got like a pipe system. I usually just draw one, but maybe one of these I just kind of click better than the other. No, okay. Something like this. Okay. And I've got like water flowing through. So let's call this like maybe I shouldn't have done 2. Here, let's call this area 1 and area 2. Let's call this speed 1 and speed 2. Okay. Also have a little fish swimming around inside this pipe system. Little fish swimming around. Things like that. Now, if you're pumping water through, and water is basically incompressible, so we're just going to go with a simple case of like an incompressible fluid like water. Do you guys think that the flow rate has to be the same everywhere? Oh, but I mean, that's what this would be, right? Conservation of flow. The flow rate has to be the same. So that could be like volume per time, like the volume per unit time in this pipe is equal to the volume per unit time here. Okay. Like in the States, we might call that gallons per minute. Okay. Or we're pumping through like 100 gallons per minute. It's 100 gallons per minute here. That's also 100 gallons per minute here. In the metric system, you might say cubic meters per second, and that would also be conserved. Okay. Now, volume, could that be this cross-sectional area times some length, right? Like some times some value like x, right? Call this maybe x1. This could be like the equal volume over here. Call this like x2, right? So I'm going to replace this volume with like area times x. And this could be area 2 times x2. Or sometimes in the notes I do length, like some kind of length that it moves. Okay. Okay. Now, why am I splitting up like that? Because of this right here. Guys, what is distance per unit time? What's that called? That's that speed, isn't it? That's that speed. So area 1 times speed 1 is equal to area 2 times speed 2. Right, there you go. That right there is your conservation of flow. Okay. So the fact that volume per time is conserved. Okay. Now this is true for as long as density doesn't change, which is pretty true for water. Now, if you're talking about air, right, air is like gases. Gases are compressible, so you have to also include a density factor for something like that. But we're just going to focus on this one for simplify this a little bit. Okay. Okay, so let's see if you guys are following. If the fish goes from the little pipe to the big pipe, what happens to the speed of the water? Does it speed up or slow down? Little pipe to the big pipe. Speed up or slow down? Has to slow down. Okay. And tell you what, if that's not immediately apparent, one trick I tell you guys that it's good to get out of a class like this is to take variables to extremes. Like if an incremental change isn't super obvious, then you could take it to extremes. What if you have a little tiny straw with water flowing through it, and it leads into like the Mississippi River? Right? It could be like something skinny to something really wide. Okay. So when that fast-moving fluid, when it hits the Mississippi River, it's not going to change the speed of the Mississippi River, or what if like Lake Michigan, right? Just comes to almost a dead stop, right? It's not really going to change. Right? Okay, so that could be an extreme example of this. Right? You could go the other way. What if you have a large pipe leading to a small pipe? You guys see the water has to speed up through the small pipe. Is that okay? Now that's just conservation of flow. What does that have to do with whatever this Bernoulli principle is? Okay. Here I got a. I'm going to lead into this with a demo. Right. I'm going to have this paper here. I'm going to blow a stream of air over the top of the paper. Blow a stream of air over the top of the paper. Now, when I do that, is that going to push the paper down, or is it going to vacuum it up? Let me see, show hands. How many of you guys think if I blow a stream of air across the top, it's going to push it down? Who thinks it's going to push it down? Who thinks it's going to vacuum it up? Going to vacuum it up. Ooh, okay, so it seems about 50-50 split. Let's try that. Try this guy on camera. You guys see it? It's like vacuuming up. You guys see that? Huh. Okay, so interesting that moving fluid actually vacuums up the paper. Now, going back to this fish in the pipes, that's making me think, the fish was going from a slow-moving fluid to a fast-moving fluid. This fish is going to feel a pressure change. What do you think the pressure change that the fish feels is going to be? It's going to be high or low pressure right here. What do you guys think, based on what I just did? Let's see, a fast-moving fluid just did what to the pressure? It lowered the pressure, right? Didn't like vacuum the paper up. I bet the fish is going to feel a very low pressure inside the small pipe and a relatively high pressure here. I bet that when the fish goes from here to here, from the big pipe to the small pipe, and the water speeds up, it's going to feel like it went from the bottom of the pool to the top of the pool, or vice versa down here, from the top of the pool to the bottom of the pool, right? Even though it's not actually changing its height, right? It's horizontal the entire time. So what the heck is up with that? Well, I need to go back to first semester. Do you guys remember conservation of energy? The sum of energy at point A is equal to the sum of energy at point B. This was a framework we used to solve lots of questions. For example, Galileo goes to the top of the leaning tower, drops the ball. How fast is the ball hitting the ground? There were a few ways to solve it. One way we solved it is we said, well, at the top, it's all potential energy. That's your MGH. Say at point A at the top of the tower. And at the bottom, it was all 1/2 mv squared. Kinetic energy. And that was at point B. Right? You guys remember that? Set that equal to that, and then you could solve for the V, and the answer was always square root 2GH. You guys remember that? Right. Okay. But if you wanted to change the question, well, maybe you could possibly have kinetic energy over here. Maybe Galileo throws the ball instead of dropping it. Now you got some 1/2 mv squared going on at point A. Okay? And maybe you're not looking at ground level. Maybe you're looking at above ground level. You want to know how fast is going like halfway up the tower. So you need an MGH over here at point B, right? And maybe you could have other kinds of energy. Maybe there's a spring involved. Right? So Galileo brought a spring gun. Now you got some other kind of energy, right? Energy plus. Okay? And then, just the past couple weeks, we added thermal energy. That was some other kind of energy also. Yeah, thanks. Is that right? Right, so now we got like a more complete version of this, right? Okay, so we got this. This is going to tie to that fish in the pipes, I promise, but it's going to take some, right? And the connection is actually going to involve this density we were talking about a few minutes. Wait, where's my? Please check my notes here. Oh, here it is. Here it is. Okay. Remember just a few minutes ago, I was telling you guys about this density is mass per unit volume. You guys remember that? Okay. Well, see, the density of water going through a pipe system, since water is basically incompressible, it has some constant density. Hey, I want to know something about the water flowing through the pipe system, not in terms of its mass, but in terms of its density. Okay, so let's do that. I need to divide this term by volume. Wouldn't that make wouldn't this mass divided by some volume? Bam, there's your density right there. You guys see that? Okay. But if I do that, you guys have bam, 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 6 terms. You guys see 6 terms? I need to do that for all 6 terms. I need to divide every single one of these by some volume. Okay. And this looks really generic, like just some generic volume, right? You guys see divide by volume for all this? Okay. So right there, bam, that's density. Oops, here's same thing with right there. There's density again. There's density. There's density. Okay. And what about this though? What is energy per unit volume? See, I know energy is in joules, which is like kilogram meter squared per second squared, right? Force times distance. Volumes in cubic meters, right? Anyway, if you work this out, this ends up being Newton per square meter. You can kind of see that, right? So this is the same thing as kilogram meter per second squared divided by square meters, which is Newton per square meter. That's a pressure unit. This whole thing is capital P pressure. Okay, this is 3-letter rho right here. Okay, so I can do this. I can say some initial pressure at point A plus rho GH at point A plus 1/2 rho V at point A squared equals, and the same thing at point B. Pressure rho GH 1/2 rho V squared. Okay, and now I have a relationship for like water flowing through a pipe system. And what are all these parts? Well, this P refers to some kind of internal pressure. So the capital P refers to the internal pressure of the water. That's like, see if my fish is swimming around in my pipe system. Dig up this fish again. Right. Remember, he'll feel like a pressure change, which has to do with like me blowing the air over the paper and like vacuums it up. So something to do with like a moving fluid, the internal pressure changes, it decreases, right? Right. Here's the density of water is rho, right? So somebody is like, do you guys think if you like pump water up to a water tower, right, there's some height change, right? There's a reason the water tower is really tall, right? Help distribute the water. Okay. And then V, that has to do with like the speed of water going through the pipe system. Okay, that could change too. Right, you guys see all that? Right. So you can start with conservation of energy, just divide everything by volume, and now you have a relationship for water flowing through a pipe system. What's the internal pressure? What's the speeds? What's the height changes possibly, if that's a factor? I guess that's Bernoulli's principle right there. That's called Bernoulli's principle. So let's switch back over here. Right. So remember, and it's been a while since we on this PowerPoint slide. Right. When I flip over there to the notes, I set up conservation of flow, and then I set up Bernoulli principle. Right. Like I said. Okay. Oh, here's Bernoulli principle. That's what I just derived for you guys from conservation of energy. That's it right there. Right. Internal energy. So like okay, so energy to internal pressure, right? Motion, what's the height change? Okay? So I've got some horizontal pipes for some examples here. Now horizontal pipes, there's no height change, so you can make it even simpler. Right? When water like goes through this crimp, it has to speed up, and the fact that it speeds up, it means it also has to be decreased pressure. Let me do a numerical example with you guys for why it would decrease pressure. Okay? So horizontal pipe system, these heights would be the same, right? there's no height change for a horizontal pipe system. So can I just knock this term out, boom, like that? Is that okay? Okay. Now let's do this. Let's do some internal, here, get pipe system. Let's have a big pipe leading into a small pipe. Slow, fast, and this fish is like moving from the big pipe to the little pipe. Okay, so there's some internal pressure plus some 1/2 rho v squared, and then on the little pipe, inside the little pipe, there's some different pressure plus some different 1/2 rho v squared. Okay, would that be true? Okay, and I'm just gonna make up some crazy numbers just to show the big principle of how this works. Okay? Let's say that this density of water is like 1,000 kilogram per cubic meter. I mean, that actually would be a realistic number, right? And let's say the speed was like 10 meters per second. Don't forget to square that. Let's say the internal pressure was like 50,000 pascals. 50,000 pascals. Boom. Okay. I wonder what would be the pressure in the small pipe. Now it should go down because the water is speeding up because conservation of flow. So we'll walk through that. That's like me blowing over the paper. But how much? Now let's say we did the conservation of flow stuff already, and maybe this pipe has half the area, which means it's going to have twice the speed. So now we're up to 20 meters per second. Okay, don't forget to square that. Okay. Let's get some numbers going. Okay, how many pascals are we talking about here? So 1/2 times 1,000 times 10 squared. Okay, so this was also 50,000. So we got 50,000 pascals of just internal pressure plus 50,000 pascals that were diverted into the fact that it's a motion. Okay, it's equal to. Okay. Then on the right side, what's 1/2 times 1,000 times 20 meters per second being squared? This is now. All right, I chose some bad numbers, but actually maybe it'll really be a good example. Oops. Okay. Twice the speed is like 4 times the kinetic energy. Okay, so we've got 200,000 pascals. Okay. Ooh. So do you guys see the balance of this? Yeah, it's like negative 100,000, I think. Oops. Okay, we went negative pressure. Now, gases can't go negative pressure, but weirdly enough, water or liquids can. Liquids can go negative pressure. I didn't mean to do that, but actually, I'm about to make a good point with this too. Okay, so you guys that? Okay, so if you go from a big pipe to a little pipe, water speeds up and then the pressure drops. Okay, oops. Share my screen there. There you go. Share screen. Okay, so back over here then. Right, that is here, you can see that in this Venturi effect over here. You guys see a big pipe leading to a little pipe? Okay. Now they have 2 different liquids here. I don't know what the liquids are. Maybe it's like water and mercury, or maybe it's ethanol and water. I don't know. Right, so we got 2 different liquids. You guys see that? Now the fact they have the top fluid flowing right to left doesn't actually make a difference to this outcome. You could have it flowing left to right and you get the exact same pressure differential. You guys can say being pushed down on the right side and being vacuumed up on the left. Right? That's exactly consistent with all the notes I've been giving you guys, because the water, maybe we'll call it water, right? So the water on the right side is flowing slowly, so that's a high pressure, right? And the water on the left side is flowing fast, so that's a low pressure. See how it gets vacuumed up on the left and pushed down on the right? Pressure differential. Now you can look at that pressure differential. If you know the densities of these 2 liquids, and you know the areas of the pipes, you can calculate how fast it's flowing. Now, again, you wouldn't know if it was flowing right to left or left to right, but you could calculate the speeds. Okay? That's called Venturi effect. Another example of Bernoulli's principle is airplane lift. Right? So if you look at an airplane wing, there's actually more area on the top than on the bottom, just like this picture. You see more area on the top than on the bottom. So that when air is flowing over the wing, it has to move a greater distance over the top than the bottom. Therefore, it's flowing faster on the top and bottom. Therefore, there's less pressure on the top and the bottom. That helps give the plane some lift. That's how planes fly. Okay. But one of the ways. Okay. Okay. So remember my example I just made up on the fly? It came out with like a negative pressure. Oops. Okay. What do you guys know happens to water if you make the pressure too low? What does it start to do? It starts to boil, right? So it's going to boil and like evaporate. Right? Even though it's not hot, it could be room temperature. It could like boil away. Right? So engineering term for this is called cavitation. You can run into this into pumps, because if you're pumping a bunch of water through, say, like a mechanical gear system, Yeah, there could be places near the teeth of these gears where the water's moving really fast. If it's moving too fast, then that's going to lower the pressure too much. Well, yeah, it will actually start to boil inside the pump, and it can actually like destroy the whole pump. And you guys see that right here. So that's called a cavitation. So cavitation right there. Right. What else we got? Okay. Yeah, states of matter. So 3 main states of matter, you guys know: solid, liquid, gas. You guys know basic properties of those. Liquids and gases are both considered fluids. If I say fluid, I might refer to either of those. One property that distinguishes the gas from a liquid is gas will usually occupy whatever volume of the container that's in. So you can compress in gases, but usually you can't with liquids, right? But you can keep heating a gas and it will eventually ionize. So the electrons will be stripped away from whatever nuclei they're growing about, right? Actually, you can keep heating a plasma and that will eventually like tear apart the atom even more, but won't worry about that so much, right? If you go to the other extreme, you can actually cool a solid down near absolute zero and it undergoes a phase change to something called a Bose-Einstein condensate. But you have to get like a crazy fraction of a degree above absolute zero for that to happen, where the atom like collapses on itself. They've actually created that in labs, Bose-Einstein condensate. That's if you make it too cold, right? Here's some examples of some plasmas. When I flip on the fluorescent lights here in a minute, fluorescent lights, there's electricity being sent through a bulb. That's ionizing gas. So that's an example of plasma. Sun, stars, plasma. Okay. All right, but those about rain. So let's cut that right there. All right, so good plasma. You guys ready for lights? Lights. Ooh, there's some plasma right there. All right. Call that a day.